end behavior, which again is the same idea as taking the limit as x approaches positive and negative infinity of a function, or sometimes just one of those, tells us what's happening to a function as x gets increasingly large. Or in the case if we're dealing with negative infinity, what happens is x gets incredibly small. So this has practical implications to let us look at things like average cost over time. So for instance, in our first example, a company is planning to manufacture snowboards. The fixed costs are $100 per day. Total costs are $5,900 per day at a daily output of 20 boards. So assuming the total cost is linearly related to the total output per day, we first need to set up an equation for the cost function. So the key here is a piece of information that there's a linear relationship, meaning we need to set up some function of the form y equals mx plus b. That's slope-intercept form. First thing we can pick up on are the fixed costs, the $100. So that fixed cost is always going to be our value for b, the amount that's unchanging regardless of what x is. So that fixed cost is always just $100. But that doesn't give us our slope. So to get our slope, what we can do is look at the fact that we know total costs should be $5,900 a day with an output of 20 boards. So that means our total cost, y, with a production level of 20, would allow us to make some substitutions here to write this as 5,900 equals m times 20 plus 100. And then from there, we can solve for m. So we would subtract 100, divide by 20, gives us a slope of m equals 290. So this gives us a cost function, c of x, equal to 290x plus 100. Now that we have that function, in part b, we can set up the average cost function, c bar of x, which is just the cost function divided by x. So we take our original cost function, put that over x, and then we want to find the limit as x approaches positive infinity of that average profit function, or I'm sorry, average cost function. So to take the limit of that average cost function, we can open up Wolfram Alpha and find the limit of 290x plus 100 divided by x as x approaches infinity. So first verifying that again our problem is set up correctly here. We see that we get a limit of 290. So that limit will be 290. In part C, we want to sketch a graph of the average cost function. So we can get rid of that limit statement that we put in and instead say graph 290x plus 100 divided by x, and then we're given a domain of x between 1 and 30. So for 1 less than or equal to x, less than or equal to 30. And then Wolfram Alpha is going to output that graph, which we can see curving down and approaching closer and closer to a value of about 290. So we get a graph that looks something like this, and since the limit as x approaches infinity, is 290. That means we're going to have a horizontal asymptote at y equals 290. Then the last question we're being asked here is, as snowboard production increases, the average cost per board approaches to what? So that's basically saying as x, which is our production level, increases to infinity, our function value is approaching, in this case, that average cost of $290 per board. In example 5, we have a question where we'll consider a similar type of problem, but in this case comparing two different models, an energy efficient model and a conventional model. So we know the energy efficient models are more expensive to make, cheaper to operate. So the cost of purchasing both of these models are provided below. We want to first express the total cost and the average cost of purchasing and operating an energy efficient model for X years. So our cost function in this case is going to be simpler to come up with. We have an initial cost of $800 plus a variable cost of $54 times X to come up with the marginal average, or I'm sorry, to come up with the average cost function. We'll take our cost function and divide that by X. So similarly, for the cost of our conventional product, we have an initial cost of $740 plus the variable cost of $69 per year. To get the average cost, or the average cost function, we again take that cost function and divide it by X. In part C then, we want to find the limit as X approaches infinity of our average cost function for the energy efficient model. So you can switch back over to Wolfram Alpha, repeat the same process we did in the last example, but this should give you a value of 54. Take the limit as X approaches infinity of the average cost function for the conventional model. Should give us a value of 69. And then we want to provide an interpretation for what this means. So the result in part C implies that over time, so not initially, but as time passes on, the average cost for purchasing and operating the energy efficient model, since that's approaching a cost of $54, is going to be cheaper than that same purchasing and operating a cost for a conventional model.